A practical design of a gyrator circuit is shown here using two ideal op-amps and 7 impedances that would be just simple resistors. We want to show this relationship between the currents and voltages of the two port as shown here. Basically, this matrix is saying that V2 is equal to negative ZI1 and V1 is Z times I2. So it's a very interesting relationship in the sense that voltage of the second port is related to the current of the first port and vice versa. If we can prove it, then we are effectively realizing a gyrator, and it has a lot of applications. And this is a practical design of a gyrator because the supply voltages of the two op-amps can be shared, so you don't need two separate set of supply voltages. That's one huge benefit of this practical design. Let's make the assumption that op-amps are properly biased. They are not saturated. They are operating in linear region of operation with dominant negative feedback. As a result, we can make the assumption that virtual short is valid for both op-amp. So with virtual short valid, we can write that the voltage at positive input terminal of the op-amp is equal to the voltage at the negative input terminal of the op-amp. So let's name this as equation 1. I'm going to use it. Okay, so look at the op-amp number 1. We are applying V1 at the between the positive input terminal and the common node, this node at the bottom. Because of virtual short, this V1 should also appear between the negative input terminal and the common node, which means V1 appear across this impedance Z. So if that is the case, it results in a current flowing through this impedance Z Ix that is equal to, so Ix is equal to obviously V1 divided by Z. Let's refer to this as equation 2. Okay, this Ix cannot go through the input terminal of the ideal op-amp because it has infinite impedance. So Ix has to go through this branch, which means through this Z. Now, the trick is for this Z and this Z, you can see that they both have a common node here. And also on the other side, the voltage here is V1 because of virtual short, and V1 is also here. So what I'm trying to say is this impedance Z and this impedance Z, they are the same value. At the same time, they have the same voltage drop across them. Therefore, whatever current is going through this lower one should go through upper one as well. So here we have Ix as well. All right, so what's the benefit? This I1 coming in cannot go through input terminal of ideal op-amp because it has infinite impedance. Therefore, I1 has to go upward. So you can see that I1 arrives at this node, Ix arrive, and then the sum of them, because of KCL, goes through the upper branch as I-Vi. So what I'm trying to say is I-Vi is equal to I1 plus Ix, which from equation 2 is V1 divided by Z. This is equation number 3. Okay, so this I-Vi flows through this resistor Z and result in a voltage drop, which we can easily compute by just multiplying I1 by Z, and then we get to, after voltage drop, we get to V2, because V2 is the value of this node, which is the other side of Z. So on one side of this impedance Z, we have V1, as is shown here. On the other side, we have V2. So what I can say is the voltage drop across, so basically V2, the other side of this impedance here, so here you have V2, is equal to V1, which is the left-hand side, minus the voltage drop, which is Z times I-Vi. Okay, so as a result, I can say V2 is equal to V1 minus Z, and I'm using equation 3 now to substitute for I-Vi from what I see here. So Z times I1 plus V1 over Z. Okay, almost done. You can see that this cancel out the V1 here and the V1 here cancel out each other. So what I get is V2 equal to negative Z I1. Great. Let's name this equation number 4. And that's exactly one of the two equations I wanted to prove. So we got one. Okay, so for the other one, let's see what we have. This current I2 comes in. It cannot go this way because it will hit the input terminal of ideal op amp, which has infinite impedance, so it cannot go that way. On the other side, IY comes in. So the sum of I1, IY, and I2 goes here. Okay, so this current that I can refer to as I alpha, let's say, or I, whatever you would like to name it. So this current, let's name it I, um, let's say alpha. I alpha is equal to, maybe I use a different color so that it's easily visible. So the current I alpha, okay, the current I alpha is equal to I2 plus I y. That I know. Okay, that is helpful. Now, the other observation I have is this one. The voltage here at this node, as you can see, because we have V1 here, and because V1 appears across this Z with Ix going through it, and Ix again goes to another Z, so it becomes 2 times V1, obviously, because 2 times V1, we have a drop of V1 here, and then we have another drop. So 2 times V1 we have this side. On the other side, because of mutual short, V2 is here on the positive side, and V2 should be on the negative side as well because of mutual short, as long as the circuit is in linear and op-amp is linearly biased. And of course, nothing goes to the terminals of op-amp, ideal op-amp, because of infinite input impedance. Now, the voltage drop across this Z is 2V1 minus V2. So 2V1 minus V2. That causes a current to flow through this resistor. So that same current, there is no way for it to go, and the only way it can go is continue going upward to this impedance Z, and then as a result it will cause a voltage drop across that impedance. Let me just have enough space here. Okay, so we will have the same voltage drop because these two impedances are the same and the same current is flowing through them. So the voltage drop here is also 2V1 minus V2. So the interesting thing is on the left-hand side of this impedance, we have V2, and the voltage drop that we observe is also 2V1 minus V2. So here, this voltage can be computed, and it's simply V2, this value, minus the voltage drop across this impedance, which is 2V1 minus V2. So 2V1 minus V2. And you can see that it becomes 2V2 minus 2V1. Let me just clean this up here so that we have enough space to write this, otherwise it becomes hard to see it. I'm going to move this I alpha here so that I have enough space to write this. So I got to 2V2 and minus 2V1. So that's the total voltage at this node here. Okay, so the nice thing is now I know the voltage drop across Z because on one side you can see it has a voltage V2. On the other side it has this voltage. So as the last step I can say this voltage drop plus minus, however you want to name it, plus minus V alpha. So the V alpha is equal to V2 on one side of that impedance minus on the other side you have 2V2, the value here, minus 2V1. is equal to, obviously, if you just simplify things here, it becomes 2V1 minus V2. So now this voltage drop is equal to the current that is flowing through this impedance, which is I2 plus I times the impedance. Now, I am going to use what I found here, equation 3. So from equation 3, I'm going to substitute for I. Basically, what I get is 2V1 minus V2 on this side is equal to Z times I2 plus I1 plus V1 over Z. Okay, the nice thing is you can see that we get V1 here, and that V1 simplified with 2V1 on this side. So what I'm going to get is V1 minus V2 is equal to Z times I2 plus Z times I1. Now, what is the benefit of this? Well, I can go back to equation 4. Z times I1, according to equation 4, is negative V2. So what I'm having here is, according to equation 4, I can cancel out negative V2 with Z times I1. And as a result, what I have remaining or standing is V1 equal to Z times I2. That's the last equation, the second equation that I wanted to prove. And that concludes that this circuit is really a gyrator. Combination of 4 and 6 does the job. Gyrator is very useful, and this is a practical design of it. And the symbol for gyration or gyrator is this symbol. So if you see this circuit symbol, it's exactly effectively just a symbol for this 2 op-amp circuit. It's a two-port. You have plus minus V1 on one side with current I1 flowing in. You have plus minus V2 on the other side with current V2 I2 flowing in. So let me just make sure it is written nicely. So it is plus minus V2, and then you have current I2. And whenever you see this symbol and these two currents for the two ports, it means that we are realizing this matrix of relationship, basically voltage controlled current sources, in a way that the voltage of one port depends on the current of the other port and vice versa. As shown in other videos, there are many benefits for these kind of circuit. In one simple realization, we can just substitute all Z value with simple R. In that case, the matrix becomes minus 1 over R and 1 over R, in which we refer to R as or Z as the parameter of the gyration, or impedance of gyration, or resistance of gyration. And naturally, 1 over R or 1 over Z can be referred to as gyration conductance or admittance. I hope that this is helpful in terms of showing how practically we can realize a gyrator. And of course, from this point on, we can use this circuit as this symbol and come up with combination of more complicated circuits with multiple gyrators inside.